First of all, we need to know what thermodynamics is all about. Thermodynamics is a science, but more importantly, it's an engineering tool used to describe processes that involve changes in temperature, transformation of energy, and the relationship between heat and work. It is also used to describe the performance of propulsion systems, power generation systems, refrigerators, and to describe fluid flow, combustion, and many other phenomena.
There are four laws of thermodynamics, and they are some of the most important laws in all of physics. But first, we must get familiar with some concepts. First, there's heat, that measures the amount of energy transferred from one body to another because of the temperature difference between the bodies. Next, there's internal energy, energy that a body possesses due to its temperature, caused by molecules on a microscopic scale. Then there's work. Work measures the amount of energy transferred to or from a body or system as a result of forces acting upon the body, causing a displacement on the body. It's the product of the displacement of the body and the component of the force in the direction of the displacement. No displacement equals no work. And last, there's the law of conservation of energy, which states that the total energy of an isolated system remains constant regardless of changes within the system. Energy is a quantity that can be converted from one form to another but cannot be created or destroyed, according to Einstein. An isolated system is a system that doesn't interact with its surroundings in any way, so the internal energy and mass of such system are conserved.
Zero law of thermodynamics states that if two thermodynamic systems are each in thermal equilibrium with a third, then they are in a thermal equilibrium with each other. Or in other words, objects in thermodynamic equilibrium have the same temperature. This means that if you bring two objects, one hot and the other one cold, the heat will flow from the first to the second one until both are in the same temperature, or equilibrium.
Let's imagine we have a big glass of water with some ice on it. This glass of water is at a temperature of 3 degrees Celsius. Let's imagine we leave this glass of water outside on a sunny day. The temperature outside is of 30 degrees Celsius. The zeroth law of thermodynamics says that eventually the water will reach the temperature of the environment. This is called equilibrium.
Remember Einstein's law of conservation of energy? That energy is a quantity that can be converted from one form to another but cannot be created or destroyed? Well, then the first law is a consequence of the law of conservation of energy. And the first law requires that a system may exchange energy with its surroundings strictly by heat flow or work. Like light bulbs, they transform electrical energy into light energy, or gas stoves that transform chemical energy from natural gas into heat energy.
Now, this first law of thermodynamics results in this equation, where delta Q, or change of heat, equals W, which is work, plus delta U, which is the change of internal energy in the system. Now, we are working with what we call closed systems, which means that they don't let heat in or out, as they are closed. And in such systems, there is something called ideal processes, which are the next ones. An adiabatic process in which there is no heat exchange in the system, delta Q will equal 0 joules. Next, in an isothermal process in which there is constant heat throughout the process, delta U, which is the change of energy in the system, will equal 0 joules. Next, an isochoric process or an isovolumetric process in which the volume is constant, the work made by the system will be equal to 0 joules. Finally, an isobaric process where the pressure is constant throughout the process, work will equal the pressure times the change in volume in the system, or delta V. And now, we're going to solve a problem using the concepts we just learned. While doing 500 joules of work, a system of ideal gas expands adiabatically to 1.5 times its volume. A. Does the temperature of the gas increase, remains the same, or decreases? And B. What is the change of the internal energy of the system? The problem already states that the work of the system will be equal to 500 joules. As this process is adiabatic, delta Q will be equal to 0 joules. We're going to make a substitution in the equation. Where delta Q will be equal to 0 joules. The work will be equal to 500, and U is the variable we are going to solve for. In this case, the change of internal energy will be equal to minus 500 joules.